point out that, resume, go, okay. We'll start with like y equals x plus 9. So this is a function because it says that it tells us how to get an output given an input. And so that makes it a relation. We know it's a function because if I pick any specific number and I add 9 to it, it is impossible for me to get more than one number out of that, right? Like there's only one number I can get as an output if I use a specific input and add 9 to it. And so this equation describes, or I like the word represents better, represents the function defined by the rule add 9 to your input to get the output. So notice that the definition of the function isn't the equation itself. That's just the symbolic representation of it. The function itself doesn't say anything about x and y, right? The function is just a rule. It says if you want to get an output, add 9, I used 7 last class. Add 9 to your input and that'll give you the output you're looking for. So it really has nothing to do with the variables themselves. So we want to start thinking of variables just kind of as placeholders. Like all they do is like take the place of input and output, so we don't have to write like output equals input plus 9, which would get kind of annoying to have to like write those words every time. So our variables are really just like kind of like dummy inputs and outputs. And if we focus on the rule a little bit more than the variables themselves, it becomes a lot easier to move, like to use this notation, like regardless of what items we try to use as inputs and outputs. So like it's easy to get caught up on x's because we use x so often, but really x is just a dummy input. It's just like something that's taking the place, like standing in for whatever input we're going to use later. So we're going to express this symbolically in a different way, which we call function notation. And it looks like this. So this is red f of x equals x plus 9. So the equals x plus 9 part is kind of boring, but the left side, this f of x, there's a bit to unpack there. So what this tells us is the name of our function. So f is the name of the function, which is important to remember because f is not a variable. Like we can't do anything mathematically with f itself. So it's just like if I plugged Amanda into that equation, like it wouldn't really make any sense mathematically, right? Like you can't do mathematical operations with a name. So f looks like a variable because it's a single letter, but really it's just the name of our function, and we can't treat it as a number or do calculations with it. So this isn't f times x. It's that whole symbol represents one thing. Part of it is the name of the function, and then the other component is the input. So this tells us what input we are putting into the function. And then together, this whole symbol represents the output of f corresponding to an input of, I don't like that wording, the input x. So if anything was on the left side was going to be thought of like as a variable that represents some value, it would be like that whole symbol, f of x, represents the value of the output. And then the last piece of this whole thing is just the rule. We can also think of that whole thing as the output of the function because it's equal to the output of the function, right? So like both sides represent the output of the function. When I first learned about functions, it was always in terms of like machines. Like functions are just like machines that you put something in, it like does something to whatever you put into it, and then it spits something out, right? So there's these like little diagrams people like to draw. So I'm going to take x and put it into my function, which is named f. I'm not a very good artist, so my old math teacher drew really pretty pictures of machines, but I do not. And then it's going to spit out f of x. So in this case, what this is doing is it's adding 9. This is my input. This is my function. And this is my output. Any questions just about like what any of this means? So far so good? We'll use it a bit now, so it'll make more sense. But in general, like the sort of the first like key thing you want to remember is just that notation isn't f times x, so it's not like something where you can like solve for f or something like that, right? Like it all comes together. We can evaluate, so let's find, we'll do f of 3. So what that's saying is find the output of f that corresponds to an input of 3. So I would say f of 3, as soon as I see the 3 in those parentheses, that tells me that I am applying the rule add 9 to the number 3. So I have 3 plus 9. Note that these guys always match, right? Whatever your input is on the left side has to also be what you're applying the rule to, and vice versa. Like we couldn't say f of x equals 3 plus 9. Because f of x equals x plus 9, right? If the input's x, we're adding 9 to x. If the input is 3, we're adding 9 to 3. If the input is like a house, we're adding 9 to a house. Like, does not matter what it is we put in those parentheses. That's what we have to apply the rule to. And vice versa. If we're applying the rule to 3, we can't put something else in those parentheses. So, going along with that, like the left side of this is just as important as the right side. So just like when you solve an equation, you write like the left and right side of your equation on both in every single step. The same is true when you're working with functions. Like, yes, I know that we could just be like 3 plus 9 is 12 and like write the number 12 and put a box around it. Like, so this is what I mean about notation being like the most important thing today is like, I don't really care that 3 plus 9 is 12 so much, but I care about like the notation and developing that. So writing the left side is just as important as doing the calculation on the right side. So we end up with f of 3 equals 12. And the beauty of function notation is that this one little compact statement tells us a ton of stuff. It tells us what input we used, it tells us what function we applied to it, and it tells us what output we got, right? So when you, like, it's not that profound in this setting because, like, it was like a 2-liner, right? But when you start doing problems that are like 2 pages long and you have multiple functions, if we called all the functions y equals, it would get really confusing really quick, like which function we're using where. Whereas if one of them's f and one of them's g and one of them's h, then when we get to the end, we know which function we use, we know what input we started with, even if we started with it like 2 pages ago, and then we know what our final like answer is, right? So like this whole statement like tells us everything we need to know without having to sift back through everything we did to be like, oh wait, what did I use there and what did I use there? And like it's easy to get lost and all that. This is the same as saying that the point (312) is on the graph of f. So if we were to graph the function f, in function notation, we have our x value and our y value, and then it tells us which graph it's on, so which function. So just like ordered pairs, it shows us that correspondence, but then gives us the added benefit of knowing which function we used. So let's look at a couple other ones. Let's let g of x be, say, 4 times x minus 3. And we'll start by just finding g of, say, -2. So to find g of -2, all that's saying is apply the rule to an input of -2. So we have g of -2 equals 4 times -2 minus 3. So g of -2 equals, what is that, like -20. Now the input of a function doesn't have to necessarily be a number, nor does the output. So I can evaluate a function for another variable, for like a whole expression. So let's try, we'll find g of x minus 1. So all this is saying is apply that rule to x minus 1. So our rule says subtract 3 and then multiply by 4. So I'm going to just say 4 times x minus 1 minus 3. In general, you always want to put your input in parentheses, although in this case, like as soon as we write it, we see that like those parentheses aren't actually doing anything for us, right? The ones around x minus 1. There's nothing that we have to distribute to the x minus 1 alone before we can subtract the 3. And so in this case, we could just drop those parentheses. But is everybody cool with how we plugged it in? Any questions about that? So 4 times x minus 4. And that's all there is to it. Like, we can't go any further than that because we don't have any additional information. So like I said, like your output and input aren't always going to be just like a number, right? You can get an output that's an expression depending on what you used as your input. So far, so good. I feel like you guys are quiet. I don't know if that means you're bored or confused. We good? Or just so interested you can't even, like, formulate words. Oh. Yeah, I figured. Okay, so let's go the other direction. So let's start with a rule, and then we'll write a function to match our rule. So we're going to do... We'll say that the function h is defined by the rule. What did I say it was defined by? There it is. Multiply by 5. And then subtract 3. So what this rule is doing is it's telling us what to do with our input in order to get our output. So we want to start, in order to write this in function notation, we're going to start with the left side. So we need the name of our function, which is given right here. So the name of our function is h. And then we just have to pick like a dummy variable to represent our input. I mean, 99.999% of the time people pick x, but like you could pick really whatever you want. I'm going to just go with convention and pick x. So h of x equals, and so when I put that x in those parentheses, I'm saying that I'm using x as my input. So I'm going to apply the rule, multiply by 5, then subtract 3 to x. So I'll start with x, multiply it by 5, and then add 3. And you could have written like x times 5, like the order of that doesn't matter. We're just sort of like 5x is sort of what we're used to seeing, right, when we're multiplying 5 by x. And so that's my function. Good? Okay, you guys try this one. So let's say the function let's call it w is defined by the rule subtract 3 then multiply by 5. So go ahead and write yourself a rule in symbolic notation using function notation, and then compare it to h of x, because if you wrote the same exact thing on the right side of your function, then you want to go back and think about the order that this is happening in, right? So order of operations is given in the sentence, but we want to make sure that the order of operations implied in our expression reflects that. So I'll give you a second to write it. Okay, so what should this look like? Very good. So w of x, again, notice the name of my function is w. It's really tempting to like write something like f of w, because as soon as we see function, we think f, because it's the most commonly used one. But you want to be really careful not to invent like new names, because if you write f of w, you've made w your input, not the name of your function, right? So we have w of x equals, so we took our input and subtracted 3, and then anytime you do addition or subtraction before multiplication or division, you have to put it in parentheses so that you're telling yourself or whoever's looking at this that that subtraction is happening first before the multiplication, because without the parentheses it would be exactly the same as the first one, right? And order of operations would say multiply first and then subtract, and so those parentheses are really important to actually reflect the order that we're given in the statement of the problem. Let's talk about net change, and then we'll come back to w in a minute. So the net change in f, in the function f from A to B is the change in the output when the input changes from A to B. So we'll write this symbolically in a minute, but let's start by just looking at what it looks like graphically so we can get an idea of like what we're actually finding here. If I have a graph of just some like random function, let's say it looks like, I don't know, that. And we'll say, so I have an x value of A and another x value of B. And there's a point on the graph that corresponds to each of those x values. And then like the y value of each point is just the output of the function corresponding to whatever input the x value is, right? So this y value is going to be the output of the function f that corresponds to an input of A. And then this y value is going to be the output of the function f that corresponds to an input of B. So when we find the net change, we are just finding this distance right here. So this is our net change. I think we talked a little bit about like when we were talking about intervals, how like you always want to think of like walking along the number line like from left to right. So the same is true in 2 dimensions. Like you always want to think of moving along these curves from the left to the right. And so we're talking about as we walk from A to B, like what happens to the height of that curve, right? So what's just the overall change in the height of those 2 points? Is that, in this case, is it going to be positive or negative? That change. Positive, right? We're going up. So notice that in order to get a positive number, you have to do the bigger number minus the smaller number, right? And so symbolically, what this looks like is, let's see, net change in F from A to B equals the bigger one, in this case, minus the smaller one. So it's always going to be the output associated with the rightmost point minus the output associated with the leftmost point. So if you think again about like walking along that curve, you're doing like ending minus beginning to figure out what the change was. So it's always the bigger, or the output associated with the bigger x value minus the output associated with the smaller x value. And that's true whether the y values are bigger or smaller. Like in this case, a bigger x meant a bigger y, but that's not always the case, right? So you always want to do bigger x minus smaller x regardless of the size of the y values. So let's go back to W, which was 5 times x minus 3. And let's find the net change in W from, let's say, like -1 to 5. So again, we want to focus on notation here. Like it would be easy to just kind of like plug one number in over here and plug another number in over here and like put them together and like spit out some number. But one thing that you're going to find, again, like as things get more complex, is that doing things in pieces, like as things get more complex, it becomes harder and harder to fit them back together correctly. And so you want to try to like do everything kind of all at once, or at least write everything all at once. Like you'll do it piece by piece, like when you actually do the calculations. But if we can write it all at once, then we don't have to figure out how to put it back together later on. So we're going to write W of our bigger x value, what did I say it was 5, minus W of our smaller x value equals, and then I usually just like group them in brackets to kind of separate the two. So first I have to figure out the output associated with an input of 5, so I'm just doing 5 times 5 minus 3. So this is my W of 5, and then minus, so now I want to evaluate for -1, so 5 times -1 minus 3. And this is my W of -1. And you don't have to label those like that, like I did, I was just showing you. And so now I'm just going to calculate inside each bracket and then subtract. So we get equals 2 times 5 is 10 minus -20. And you'll notice the notation I used here, it's fairly common if like the left side of the whole thing is more complex than just like f of 2 or whatever. We often will just write it at the top and then line up our equal sign and like simplify down the right side instead of writing W of 5 minus W of -1 in every single step. And that's totally fine with me if you use that notation, as long as you actually line up your equal signs. Like if your first step is over here and your second step is over here and like your third step is on the back side of page 7, like then you need to write the left and right side of both of every single step. But if you can line up your equal signs like neatly, then it's fine to just work down the right side and like keep the left side as is. So then equals, what is this, 30? And so what that means is that as I walk along this curve from an x value of -1 to an x value of 5, that the height of the function or the height of the curve changes by 30. One thing the net change doesn't tell us is like how we got there, right? So like I know that I need a negative. I know that like -1 is over here and 5 is over here, and that there's some point right here and some point right here, and that this height is 50. And it's possible, in this case it's true, that it's a straight line from there to there. It's also possible that it goes like this to get there, right? Neither of those, like the net change would be exactly the same regardless of like how we get there in between. It's sort of like your bank account, right? Like you can get your balance at the beginning of the month and the balance at the end of the month, and you can calculate like how much your balance changed over the month, but it doesn't tell you like how much you actually spent and got in, right? If your balance changed by $5, like you could have spent $505 and then like made $500, or you could have like somebody could have handed you a 5, right? Like you just don't know what actually happened in between specifically. And so the same is true with net change. Like it only compares the outputs at like the end points. It doesn't tell us anything about what's going on in between and how it's changing. I don't know why I'm getting rid of all of it. Okay, good? Yeah. Okay. Let's look at this in terms of an application. So we'll talk about pressure. The pressure, or the function P of D
equals 14.7 plus 0.45D gives